So before I start, let me give you an introduction about what the duality theory is all about, right? Suppose I have a problem, right, with say two variables and maybe 1,000 constraints. Okay, now you see, since the problem is two variable, the number of constraints are really large. Okay, so we can solve this problem with the graphical method. Okay, because it's a two variable problem, easily it can be solved. But because the 100 constraints are there, so it's otherwise difficult to draw these 100 constraints and check for all the corner points and to find the optimal solution, right? So graphical method is there, but we will not prefer it, right? Simply because the number of constraints are really large. Okay, then the other way of dealing this problem is with with the simplex method. Okay, okay, now you see, because there are 1,000 constraints, so in order to find a basis, so suppose the rank is also the 1,000. Okay, because assume that the constraints are all less than type and something. Okay, so what we are going to do, we are going to add 1,000 artificial variables or slack variables. If it is slack variables, then it's okay. If these are equality constraints, then you are going to add artificial variables. So in order to get one feasible solution of this problem, you need to have 1,000 iterations, okay, to get one feasible solution. So it is not very advisable at this moment to apply simplex method with the basis size as 1,000, because 1,000 constraints are there. So we are taking 1,000 variables into the basis. Okay, so simply this method we will also not prefer. So instead of looking directly for the graphical method and simplex method, what happens if I have an equivalent problem? Okay, with only two constraints and say 1,000 variables. Okay, now you see, if you have two constraints and 1,000 variables, certainly we are not going to solve this problem with the graphical method, but this problem can be easily handled with simplex method, simply because we have only two constraints. So we only need to take on two variables into the basis. So basis size is very small, and then at each iteration we have to apply only one row operation, one or two row operations. So it is relatively easier to handle. Okay, so then the question is, two variable 1,000 constraint problem, we would not like to handle either with graphical method or with the simplex method. But if equivalently I can have a problem, or I can relate this given problem with another problem, with instead of instead of two variables, I have two constraints, and for 1,000 constraints, I am able to get 1,000 variables. So the dimension changes. So this problem is relatively much easier to handle. Okay, so simply this is what we call a dual problem. Okay, and this is what we call a primal problem. Okay, and then the question is whether such problem exists that we can equivalently construct such kind of problem corresponding to this given problem with two variables and 1,000 constraints, right? And then the question is, if we can construct a problem, then what is the relation between their solutions, whether we can actually create a bridge between the solution of these primal and dual problems. Okay, so this will primarily be the uh, point of discussion for today's lecture. So we are going to discuss the duality for linear programming problem. Duality theory for linear programming problem. Okay, so for this purpose, we first consider a problem, say a primal problem of the form minimize C transpose X subject to AX greater than or equal to B, X greater than or equal to 0. So now I want to clarify a few more points also. In order to study the duality for linear programming problem, which means that I am going to construct another equivalent problem corresponding to the given problem. Okay, for obvious reasons, as I discussed earlier, because of this kind of situation, that this given problem is not that easier to deal with. So we are constructing the corresponding dual problem. Okay, so in order to construct dual problem, we are not looking at the standard form or something. Firstly, we are considering the problem in what we call as a canonical form. Okay, so this is what we call a canonical form. Okay, so what is canonical form for the given primal problem? So primal problem I will write with P. So the canonical form for minimization problem is that you minimize the linear objective function subject to the constraints ax greater than or equal to b, x greater than or equal to 0. Doesn't matter right hand side is positive or negative, that's okay, we don't bother, but the variables are all non-negative. So and it is possible to convert the given problem into this form, into greater than type form. So this is what we call the canonical form for the minimization problem. Similarly, if I'm looking for the canonical form for a maximization problem, so that will be maximize the objective function subject to ax less than or equal to b, x greater than or equal to 0. So for minimization type problem, my constraints are greater than or equal to b. For maximization, my constraints are of the form less than or equal to b. Obviously, if I want to solve the problem as such, I have to convert this problem into standard form, and then I will apply my simplex method or whatever, right? But here, the objective is not to solve the problem as such, but to construct a related problem, which we are calling a dual problem. So to find a dual problem, we are writing the given linear programming problem in a very special form, which is what we call canonical form. And the canonical form is, for minimization type problem, is the constraints greater than type, and variables are also non-negative. For maximization, constraints are less than or equal to b, and variables are non-negative. Okay, so what is the dual of this problem? So dual of the minimization type problem is, so I write here the dual. So dual of this problem is, I denote it by d. So for minimization, the dual is maximizing what my variables, my constraints are ax greater than or equal to b. So my right hand side becomes the objective function. So minimize b transpose y subject to what? A transpose y less than or equal to c, y non-negative. Okay, in a couple of minutes, I'm going to explain all the dimension of the matrices and the vectors involved. Okay, similarly, for minimization type problem, my dual is, sorry, for maximization type problem, my dual problem is what? For max, the dual is minimizing b transpose y. Y is a new variable I'm introducing. You can take z also. So it's subject to the constraints a transpose y, because the problem is minimization greater than or equal to c, y non-negative. Now you can see for the dual problem, for minimization problem, the dual is maximization type, and this dual problem is itself in canonical form. Why? Because for maximization type problem, we have the constraints less than or equal to the right hand side, and variables are non-negative. Similarly, for the maximization problem, its dual is minimization, and this dual problem is again in canonical form. And you can see the dual problem is minimization type, and for minimization type problem, my constraints are greater than type. Okay, now we can see here that if there are n variables, say 100 variables here, and say maybe 50 constraints, right, in this problem, and when you're writing the dual problem, you see your right hand side is entering into the objective function. You can see, so how many vectors are in the dual problem is essentially equal to the number of constraints. Okay, so the dimension of y is equal to the number of constraints in the primal problem. Why? Because we are multiplying with the b transpose, and the component of b are actually equal to the number of constraints. And in the dual problem, b transpose y is the objective function, so y has equivalent number of variables as the component of v, which are actually equal to the number of constraints in the first primal problem. So I am actually defining a problem whose variables are equal to the number of constraints of the first problem. And the number of constraints in the dual problem, you can see, is what? It is equal to c. Okay, the number of components in the c, and how many components in c are actually equal to the number of variables in the primal problem. So we are having a transformation from number of variables to number of constraints and number of constraints to number of variables. Okay. So and in few minutes we will be understanding that actually constraints have a relationship with the variables and variables have the relationship with the constraints. Okay. So let's understand this by a very simple example here. So let me consider one example for, okay. So I consider a maximization type problem here. So maximize x1 plus 2x2 minus x3 subject to the constraint x1 plus x2 say minus x3 less than or equal to 4 minus x1 plus x2 um, say greater than or equal to 3 x1 x2 greater than or equal to 0 x1 x2 x3 also greater than or equal to 0. Okay. Now, the first thing to be noted here is that this given primal problem is not in canonical form. Why? Because for maximization problem, my constraint should be less than or equal to type. But my second constraint here, you can see, is of is greater than type. Okay. So first, I need to convert this constraint into less than type. Okay. So my canonical form. So in canonical form, so I have to consider the problem which is in canonical form. So in canonical form, my problem will become what it is: maximize x1 plus 2x2 minus x3 subject to what x1 plus x2 minus x3 less than or equal to 4. And now to make this problem into canonical form, I simply multiply with this with the negative sign. So it is plus x1 minus x2 less than or equal to minus 3, x1, x2, x3 greater than or equal to 0. So now these two problems are equivalent problem, but this problem is in my canonical form. So this is my primal problem, right? Doesn't matter if the right hand side is negative here because I'm not solving the problem. Okay. So to solve the problem, I understand that I have to convert this problem in the standard form, which is not required at this moment because I am only studying the dual of this problem. Now, what should be the dual of this problem? So dual of this problem is the minimization problem. So, okay, so let me write a little more about the matrix A here. So you can see this problem can be written also in a little elaborated form as what? So my C matrix is what? So C matrix is here, it is 1, 2, minus 1 transpose. Okay. So C transpose is a row vector as we know. A matrix is what? A matrix is 1, 1, minus 1, 1, minus 1, say 0. Okay, I take this as 2, say this as 3, just to get rid of these ones. So 3, and this is minus 2, 0. Okay. And my right hand side matrix B is what? It's again a column vector. It's 4, minus 3. Okay. So the dual of the problem is written here. Okay. So dual is the dual of this maximization problem is, so I write the dual of this problem here as what? So it is for minimizing, the dual is, so for maximizing, dual is minimizing what? B transpose into Y. So that means right hand side is multiplied with the new vector of y. So how many components y should have? So because b has to be multiplied, so y has only two components, say y1, y2. Okay. And it can be seen corresponding to the first constraint, I have my vector y1, and corresponding to the second constraint, I have my variable y2. Okay. So what is my objective function is what? We multiply the transpose of b with the vector y1. So what I get? I get 4y1 minus 3y2. Now, subject to the constraint, what? So here is A matrix. So I have to multiply A transpose into Y, because problem here is A transpose Y. So what is my A transpose Y? A transpose Y is nothing but the rows becomes columns and columns become rows. So what is so my first row is what? It will be 3, 1, minus 1, 1, minus 2, 0. So multiplied with what? Y1, Y2. So what is A transpose Y? It is 3Y1 plus Y2. So this is 3Y1 plus Y2. And it is what? From the constraint is greater than or equal to the component of C. So what is the first component of C? It is 1. It is greater than or equal to 1, because what I should write, it is greater than or equal to C. C is nothing but it is 1, 2, minus 1. So simply I am just multiplying it and equating it component wise. What is my second constraint? It is y1 minus 2y2 greater than or equal to 2. Then minus y1 plus 0y2 greater than or equal to minus 1. Then y1, y2 are greater than or equal to 0. So this is the dual of my given problem, which is in the canonical form. So this the problem, I converted the problem into canonical form, so I'm able to write the dual of this problem. Okay. Okay. So this is a tool. Now you can see the number of variables in the original problem is 3, and the number of constraints in the dual problem is 3. So and number of constraints in the primary problem is 2. So so we have number of variables in the dual problem as 2. So we had the desired conversion, as we were talking about, that if we have a large number of constraints, as you can see in the dual problem, I can have a smaller number of variables, a smaller number of constraints, and corresponding to the smaller number of constraints, I can have the number of variables on the other side, right? Then the important point here is that if I need to write the dual of this problem, okay, so which is basically dual of the dual problem, it is nothing but the primal problem. Okay, so these two problems are interconvertible, right? So that can be easily checked. So from here you can see, so if this is a maximization problem, so its dual is on this side. So if you consider this problem as primal problem, you can always write the dual problem as the same problem, because for minimizing, the dual is the maximization, and for constraints A transpose Y, so A transpose is nothing but A multiplied with another variable, say Z is less than or equal to B, which is nothing but A Z less than or equal to B. So Z and X have same dimensions, so these are dummy quantities, so it's same variable, and Z is greater than or equal to 0. Z is what my X here, so X is greater than or equal to 0. So dual of this dual is primal. Okay, so I can note here as I can write here as that dual of a dual is primal. So you take the dual of the problem, then you again take the dual of the same problem, you will get the original primal problem. Okay. Now the important point which I want to raise here is that we wrote the dual of this problem, which is in canonical form. Okay, so we were able to understand the A matrix right hand side, and we could write the conversion matrix into this form. Okay, but what about the original problem? You see, the dual I have written here is for the converted problem. This problem I converted from here, okay, in the canonical form. And then from canonical form to canonical form, I have the dual. So essentially, this is the dual of this problem. What about the dual of this problem? If you note here, the A matrix here is, see, in this case, my A matrix is what? 1, I changed it here, so it should be 3, and this should be 2, nothing. Okay, so my A matrix is what here is, it is 3, 1, minus 1, minus 1, 2, 0. So this is my A matrix here. You can check my B matrix as 4, 3. You can see the check the C matrix as what? 1, 2, minus 1. It's a column vector, right? Okay, but when I wrote the dual here is, you can see B transpose is 4, minus 3. Okay, but B is 4, 3 here. So where is this minus coming from if I am talking about the dual of the original problem? So because I multiplied the second constraint, so I had the actual conversion into this form. So if I wanted to know the dual of this problem, what is the dual of original problem? Okay, dual of canonical form to canonical form is fine. It is from the above formula. But if I want to write the dual of the given problem, for which I first converted this problem into canonical form, I must restore the values of my coefficients A, B, and C. And for that, I must understand that in the transformed problem, I should have A transpose, B transpose, and C transpose only, but not the change of the sign here. But here you can see the right hand side is 1, 2, minus 1. C vector is 1, 2, minus 1. But C vector should be, yeah, it's 1, 2, minus 1. There is no problem in C vector. But in the transpose matrix, you see it is 3, minus 1, 1, minus 2, wherever it has 1, comma 2, and in the third constraint minus 1, 0. So I have some change in the second constraint also. So how to restore this change? For this, we need to look into the things that if I change y2 with minus y2 dash, okay, so what will be my problem? My problem will become something like this. It will be minimizing 4y1 plus 3y2 dash, because I'm changing into this form. So my constraints are what? This is 3y1 minus y2 dash greater than or equal to 1. What is this? This is y1 minus y1 plus 2y2 dash greater than or equal to 2, and the third constraint is minus y1, because the other component is 0, minus y1 greater than or equal to minus 1. Okay, minus 1 plus say 0 y2 dash is again greater than or equal to minus 1. And now my y1 is greater than or equal to 0, but because y2 is greater than or equal to 0, but I am replacing y2 with y2 dash, so my y2 dash is less than or equal to 0. Okay, now this is a very, very important point to be understood here. Okay, so what I am saying is this is the given problem, right? We converted the problem into the canonical form. Okay, from canonical form to here we wrote the dual of this problem for the canonical form, and from this dual of the problem I restored the values of my coefficients. Okay, so now I can understand the net effect. Now you see, so 4, 3 is what? 4, 3 right hand side is coming into the in the objective function 4, 3, and then the cost matrix 1, 2, minus 1 is in the right hand side 1, 2, minus 1. That's fine also. And in the base matrix also we are having the transpose matrix. So it is 3, minus 1, 1, 2, minus 1, 0. So 3, minus 1, 1, 2, minus 1, 0 I have in the transpose matrix. So now this problem is restored. But the effect is that my one of the variable become negative, which is a very, very important point here to be noted. Okay, and why this happened? It happened because in the given problem, my second constraint was not in the canonical form. Okay, so what observation we are having here is that this is the given problem. Okay, we have the coefficients A, B, and C here. We only know the dual of the canonical form. So the given problem is canonical form. To the canonical form, I can write the dual. But the present problem is not in canonical form. Why? Because my second constraint is not actually in canonical form. So what we did, we multiplied it with minus 1, 2 to convert this problem into canonical form. And from there, we knew the dual of this problem. Okay, so at one point, the story is finished over this dual. But since here we have noticed that the constraints, the coefficients of the original matrices are changed. So in order to restore those coefficients, what I did, I changed my one of the variable to negative of the variable that restored my coefficients. Okay, so what was the net effect in that was my variable is less than or equal to type. So that means the overall net effect is that if my constraint violates the canonical form, so you can see in the primal problem, my second constraint is violating the canonical form. Okay, its effect is on the second dual variable, which is violating the canonical form, because in the primal problem, my dual variables need to be greater than or equal to 0, and now it is no more greater than or equal to 0. Okay, so the overall observation is, if ith primal constraint is not in canonical form, then the ith dual variable will not be in canonical form. Okay, next, the important point to be noted here is, because we have noticed that dual of a dual is primal. Okay, so the dual of this problem, okay, is again the present problem. Let me check here. Okay, so dual of this problem is again the given primal problem. So I can say these two are the dual of each other. So if I look this problem from the primal point of view, right, and this problem from the dual point of view, I can see that in the given problem, this given primal problem is not in canonical form. Why? Because my one of variable is violating the canonical form. This is negative inside. So when I will write the dual, what I will be doing, I will be converting this problem into the canonical form, which is the bottom problem here. So I will be going from here to here. Okay, and then from here I will be writing the dual as this problem, and then when I will be restoring my values, I will be multiplying it with -1, I will be getting this problem. So overall what I'm going to see is, if in the given primal problem my constraint violates the canonical form, okay, so its effect is what on the if the variable violates the canonical form, second variable here, it is violating the canonical form. So in my primal problem, or in my dual problem, my second constraint will violate the canonical form. Okay, so I have a second observation here. So this is observation 1, and then I have my second observation here is, if ith, say, primal variable is not in canonical form, then ith dual constraint will not be in canonical form. Okay, so let me explain this point with another example. Suppose I am considering the problem. So first thing, you must remember the canonical form here. That canonical form for minimization is the constraints are greater than type, and for maximization constraints are less than type. In all these cases, variables are greater than or equal to 0. So only a difference is in the sign of the constraints. So for minimization, constraints are greater than type. For maximization, the constraints are less than type. Okay, all variables are non-negative. Now let me consider one more example here. Suppose I have a problem, maximize x1 plus 2x2 plus x3 subject to x1 plus 4x2 minus x3 greater than or equal to 4, x1 plus 2x2 plus x3 less than or equal to, say, 2, then x1 greater than or equal to 0, x2 less than or equal to 0, x3 greater than or equal to 0. Now look at this problem. You see, this problem is not in canonical form. Okay, we can observe here. This problem is not in canonical form. Okay, so where the canonical form is violated, first point is what? My second constraint, because it is a maximization problem, my first constraint. So first constraint is why is not in canonical form, and secondly, my second variable x2 violates the canonical form. Okay, so what are the possible effects of this violation will be? So what will happen that my first, because first constraint is not in canonical form, so this will affect what? So first, because first constraint is not in canonical form, that means first dual variable will violate canonical form. Okay, because we have studied in the above problem that if constraint is not in canonical form, the effect is on the dual variable. Okay, so first constraint is violating means first dual variable will violate the canonical form. Then x2 violates the canonical form, then this will have an effect on what? Second, because second variable is violating means second dual constraint will violate canonical form. Okay, so now we will write the dual directly without converting the problem into the canonical form. So what should be the dual then? So if this is the primal problem, then my dual problem is nothing but it will be what? For maximization, the problem is what? Minimizing what? You see, for each constraint, because there are two constraints, I can see for first constraint I have my dual variable as say y1, and for second constraint my dual variable as y2. So how it is multiplied is 4y1 plus 2y2. So minimizing 4y1 plus 2y2 subject to the constraints. What? When I will write the A matrix is what? 1 4 minus 1, and when I'll be taking the transpose of the matrix, you will see the component, it will be the component wise multiplication. Okay, let me explain from this above example here, that when I wrote um, the transpose of this matrix, so it was 3 1. So in my first dual constraint, it was what? 3y1 plus y2. So basically it y1 multiplied with the first coefficient and y2 multiplied with the first coefficient of the second constraint. So it was 3y1 plus y2. And what about the second constraint? It is y1 minus 2y2. And similarly for third one is minus y1 plus y2. So we can see now we can have the column wise multiplication, right? So similarly, I can directly write here the A transpose Y as what? I will multiply with the first coefficient here, and first coefficient here is that y1 plus y2. Okay, and what is my right hand side vector is C. This is 1. I will write the sign later on. What is my second constraint is 4y1 plus 2y2. You can write the transpose and then you multiply, you will get the same thing. And what is the second coefficient of the cost is 2, because cost is coming to the right hand side now. And then minus y1 plus y3, and what is the sign? Third coefficient is 1 here. Now what are the effects here which we need to understand here? Because the violation is in the second variable. Okay, so the signs of the constraints are determined from the signs of the variable, as we have seen in the above example, that if any of the variable, please listen to me, if any of the variable violates the canonical form, okay, so then the effect will be on the constraints of the dual variable. If second variable is not in canonical form, that means second dual constraint will violate the canonical form, as we have seen here. Okay, second dual constraint will violate the canonical form. So it means only the violation will occur here. So what is the violation? Because the problem is minimization. So for minimization, constraints are greater than type, but for violation, it should be less than type. Okay, all other, because all variables are in canonical form, so these will not violate the canonical form. So only violation will occur at this point. Okay. Similarly, for variables, how many variables? We have two variables, and for first variable, the sign is determined from the sign of the first constraint. For maximization problem, the canonical form is less than type constraints. Okay, but because first variable, or sorry, first constraint violates my canonical form, that means my first variable will not be in canonical form. So the sign of first variable will be negative. Similarly, for second constraint, my sign will be what? Because second constraint is in canonical form, my second variable will be in canonical form. So this is directly the dual of the given problem. So the violation at the constraints and variables are actually reflected in the constraints and variable of the dual variable.
सर
Okay.
इसमें अगर
Second,
x3 पे अगर वायलेशन होता तो
so third constraint would have been violated. Okay. So in the dual problem, we have the number of constraints equal to the number of variables. If third variable would have violated, say if x3 is less than or equal to 0, so then my sign of the third constraint would be less than type. Okay. So this is all about my conversion of the dual problem. Then another last example which I'm going to explain here is with the
सर एक
unrestricted
डाउट है
variable
सर,
case.
सर एक डाउट है सर
मैं बाद में करता हूँ बेटा डिस्कस, थोड़ा मुझे एक्सप्लेन करके खत्म करने दो, लेट देन आई विल डिस्कस. Okay. Okay, so next, so if any of the variable is unrestricted, okay, or secondly, if we have, if there is an equality sign in constraints. So what we have to do in this case is that, so observation, or what we should say, a note here. So this is simply, you will be incorporating the things. So if ith primal constraint is equality, so equality, so that means equal to sign, which we have not studied above. So if there is a equal to sign in the ith primal constraint, so this will have an effect on the ith dual variable. So then the ith dual variable will be unrestricted in sign. Okay, I'm not going to prove why this happens, but you just observe these things. And similarly, if say jth primal or dual, so if it is primal, the effect is on dual. If it is dual, the effect is on the primal. Okay, so if jth or I can say, I can write in bracket as dual, or here I can write in bracket as primal. So if the effect is on primal, the violation in primal, the effect on dual. Similarly for dual, there is primal. So if jth primal, or I say dual variable, is unrestricted in sign, then the jth say dual, or I should say primal, then the jth dual constraint of, okay, so if I am writing constraint, so then it should be the variable. So let me not write these bracket things, because for that then I will have to write variables also. Okay, so let me write the things only in context with the primal problem. For dual problem, the changes are obvious. Okay, so if jth primal variable is unrestricted in sign, then the jth dual constraint will be an equality constraint. Okay, so let me explain this thing by means of example, where I will be incorporating all the changes in one problem. So this will consider all cases. So I have a problem, say maximize x1 plus say 400x2 minus 3x3 subject to 2x1 plus 7x3 minus say 47x2 minus 40x3 uh, say greater than or equal to 5, then x1 minus 3x2 plus x3 equal to 7, then 2x1 minus x3 plus 4 x2 minus 4x3 say less than or equal to 8, with x1 as unrestricted, x2 greater than or equal to 0, and x3 less than or equal to. So I have a primal problem where we have all kind of possible violations there. So what should be the dual of this problem? So simply we just have to understand this is a maximization problem. So the dual will be what? Minimization problem. And then you see for each constraint there is one dual variable. Let me explain first, then I'll be taking your doubts. So for each constraint I have a dual variable y1, y2, y3. Okay, so what will be my objective function for the dual variable? So it will be 5y1 plus 7y2 plus 8y3. Simply I multiplied with this. Then subject to constraints, what? First is because I have to multiply this as column wise, because I'm taking the A transpose time y. So it will be 2y1 plus y2 plus 2y3. I'm simply multiplying this column with the y1, y2, y3, and my right hand side will be 1. I will write the sign later on. Then my second constraint will be 7y1 minus 3y2 minus y3, and right hand side is what? 400. And the third is minus 40y1 plus y2 plus 4y3 is equal to what? For the right hand side it is minus 3. Okay, and then the sign obviously. So what is the sign of my first constraint? Now you see the sign of these constraints are determined from the sign of the variables. Okay, you see my first variable is unrestricted in sign. That simply means my first dual constraint will be equality. Okay, then my second uh, primal variable is in canonical form, because variables are non-negative, so it is in canonical form. That means my second dual constraint will be in canonical form. And what is the canonical form for minimization problem? That is greater than type. So this constraint will be greater than or equal to 400. And again, third variable is violating my canonical form again. So that means my third constraint will violate the canonical form. And for minimization, the violation is in the form less than type. Okay. And then my variables, my first variable y1, the sign of the variable is taken from the sign of constraint. So for maximization problem, my first constraint is greater than type. That means it is violating my canonical form. So my first variable will violate the canonical form. Okay. My second constraint is equality constraint. That means my second variable is unrestricted in sign. And my third variable, the sign of third variable depend upon the type of third constraint of the primal. And for maximization, this is less than type, means it is in canonical form. So that means my third variable is in canonical